guys, well, what we're looking at here is basically just three parallel rays, and we did this by just taking a regular light source and we put a little lens here to focus the light so everything comes out straight, because without this guy, you can see this is just an extended light source. There's a little light bulb in there. So we put this in to make everything sort of line up. Oops. And then we add these guys so that we get these nice three parallel rays, because we're going to start talking about lenses. And so there's two main types of lenses that we're going to talk about. The first type of lens is called a converging lens, okay? And the reason it's called a converging lens is when you put it here, you can see that there's the ray that goes through the middle stays pretty much straight. Let me straighten that out. So you can see the ray that goes through the middle stays pretty much straight, but these rays that come in from the side converge towards a point. Okay, so we're converging. Now, because these rays are coming in parallel, this point right here, this is called the focal point. Okay? And there's actually one on the other side, although we don't have space to do it. This line that goes down the middle, like this, if you could draw it straight, is called the optical axis. It goes right through the center of the lens. We usually draw it that way. So we're gonna erase that. Okay? The other type of lens we're going to talk about today is called a diverging lens. So if the converging lens made all of the rays converge, the diverging lens, which looks like this, is going to do just the opposite. So the ray in the middle stays pretty much straight through, but the rays that come through the side sort of diverge from the optical axis. And we can get this optical axis much straighter. So you can see this center line does not change, but these ones over here go back. And what we could do to find the focal length of this, you can see this has a negative focal length, is you trace these guys back, right? So you see these things come back to a point, and that's our focal point for this lens, okay? This is a diverging lens. Talk ray optics, when that's going to be using our concept of the ray to figure out how to do more complicated things with refraction, essentially, and also some mirrors. So we're going to start with something called the thin lens equation. This has to do with, so to do this we're going to have to introduce what thin lenses are, okay? And we basically have two kinds. We showed sort of a little model of it that I did live, and here's sort of the basics. We have the converging lens and we have a diverging lens that's over here. Now the main thing about the converging lens is the rays converge towards the optical axis, and the optical axis is just a line that passes through the center of the lens, and you use it as a reference. So here this yellow line represents the optical axis for both of these lenses, okay? So basically a converging lens converges rays towards the optical axis, whereas a diverging lens refracts them away. Now you can see at all of these points we have this interface, right, between one medium and another medium. And the thing that's different here is instead of this flat surface that we're used to from refraction, now we've curved it. So each place that it hits, the normal is at a little bit different angle from the incident ray. But as we get this transmitted ray, we still basically are using Snell's law to figure out this angle, and then Snell's law to figure out the transmission from this surface to get this angle. So this is really just a more complicated refraction, and lenses, depending on how you shape them and what you make them out of, tell you how that refraction is going to happen. So the optical axis is really important for the geometry. And so here's our two special types of lenses, although there's many other types. This is a double convex, right? This is a double concave. You could also have things like a plano convex, right? So this is the plane, this is the convex side, or you could have something like a plano concave, so plano is plane, and this is the concave side. But that's sort of how these lenses are set up, and we'll talk about something called the lens maker's equation in a little bit, and that's sort of how we determine how these lenses are going to work. So remember, converging lens causes parallel rays to converge, diverging lens causes parallel rays to diverge. And you'll notice the thing here is that all these rays coming in are parallel. If they're not parallel, you'll have a slightly different behavior. So this is just a very simplified model. Okay, so where do those things converge? Well, they converge at the focal point, and the focal length is the distance from, this is the lens axis, this line that we draw through the middle of the lens. This isn't actually where the light bends, but it's a good approximation when you're doing these things. So here the parallel rays come in and they all converge at the focal point, which is a focal length squiggly f from here to the focal point. Okay? Rays don't always converge at the focal point. Parallel rays converge at the focal point. Okay? The focal point and the focal length is a little bit more complicated for a diverging lens because it's sort of this backtracking. So the rays follow this path, but then if you draw backwards all of these rays, they're going to end up at this crossing at this same imaginary point, and that's the focal length or the focal point for the diverging lens, which is the distance between this lens axis or lens plane and this point called the focal point. Okay, so the focal point is the point through which initially parallel rays pass or can be traced back through. So this is when you trace them back. This is when they pass through this focal point. So image formation, remember, any image that you're looking for, like say this non-denominational pine tree, has many points, right? So this is really only representing this one point. And you can see here, none of these rays are coming in parallel. So as these rays come in, there's these three special rays that you're going to want to pay close attention to. But I want to start with sort of the idea. So this is your optical axis. Okay, this is your lens plane. Because this is a double convex lens, it has a focal length. Let's say we know the focal length, and here's our two focal points. You can draw them on either side of the lens, and it'll be important why we do that for this ray tracing in a little bit. So here's this focal length, here's this focal length, it's on both sides. We call the distance from the object to the lens plane S. Now some other books call this P, but we call it S. So these are both the same thing. And then you call this distance from the lens plane to the image, the same point on the image, this is going to be S prime. Some people call it Q or Q. Don't get confused, okay? So when we do this, we really want to figure out where this image is going to be sharp and in focus. And here, we're actually creating like a visual picture over here. So this would be something you could project on a wall like a projector. Okay, so this isn't like the image that you see in a mirror, which is a virtual image, right? You can't actually touch it, but this one you can. You can actually get the light focused on your hand, okay? So here's the image formation, and we have these three special rays. They're the ones we're going to use to do problems. So basically, if you have a ray that connects from here to the lens plane and passes through one of these focal points, it comes out parallel. Okay, it comes out straight. Okay, that's one of our special rays. The next one would be if it goes in parallel, it has to go through the other focal point. And last but not least, the easiest one, if it goes through the middle, it just goes straight. So you can see these three rays converge here, and these are the only ones that follow these rules. Everything else you sort of extrapolate from that. Okay. So remember, for converging lenses, if you are outside the focal length of the lens, okay, parallel rays refract through the far focal point, right? Because remember, there's one over here too. We don't care about that one for these parallel rays. rays that pass through the near focal point, so if they're coming in at an angle, right, those are going to come out parallel, and then rays that go through the center just don't get bent. All right, so these are our three special rays for converging lenses, and these don't work as well on a converging lens if you're within the focal length. Then they follow the diverging rules, and we'll talk about that in a little bit. But basically, if you're inside the focal length, there's no way for the lens to focus all of the rays to one point because they're already diverging too quickly. Okay, so remember, converging lenses, when you're outside of the focal length, produce real images, but when you're inside of the focal length, they're going to produce virtual images. And a virtual image is like your reflection in a mirror. It can't be projected onto a wall. You can see it. You only see it because your eyes do this backtracking thing where they connect the dots for you. But virtual images are things you see. They just don't, if you like walk behind the mirror, you're not going to be able to touch them. Okay, so here's our ray tracing steps. First, you want to draw an optical axis. Then you center your lens on the axis and you mark your focal points, and you mark both of them because any symmetric lens like this is going to have two. Okay, we usually represent the image with an arrow because we're looking at this point right at the tip of the arrow. And then we draw our three special rays, but first we figure out the distance between the object and the lens. Here's our three rays. We have one that passes through the near focal point, right? One that goes through the middle of the lens, and one that comes out parallel, okay? And we know what these are going to do. If we go through the near focal point, it should come out parallel. The one that goes through the middle doesn't change, and the one that goes in parallel should pass through this focal point. So we can see this is what's going to happen, and we end up with this new focused point. So whatever point was here is now here, and we end up with an image which is a distance S prime from our lens axis. Okay, so there's some geometry that happens here, several triangles, but the key takeaway here is that we end up with this interesting phenomenon. So this is the magnification. We'll talk about the geometry in a second, but it's going to be S prime, right, over S is equal to H prime over H. And there's a negative here, and this is pretty important. Now, you'll notice magnification is really just how does this compare to this, okay? So you're going to say, okay, this part makes sense because we want to know how this arrow compares to this arrow, but why would we care about this S prime over S? And the reality is when you're doing these types of experiments, usually this and this are much bigger than this and this. So when you're doing this in an experimental setting, measuring S and S prime should be a lot more accurate than measuring H and H prime if you're dealing with very tiny images. Think about like a microscope, right? Figuring out the magnification of a microscope, it's going to be much harder to measure these tiny images. Now this relationship here comes from some geometry. You can see these are similar triangles, so your tangent theta is going to be H over S or H prime over S prime, depending on which triangle you're on. And so when you rearrange this, you end up with this. Okay? And the negative is important because you can see over here, this H and H prime are pointed in different directions, so this real image is going to be upside down, okay, which is something you could check by using any kind of converging lens to focus an image. So that negative has to be included in the SS prime because neither of these lengths are considered negative. So the magnitude tells us the ratio of H to H prime, and the sign of M, of the magnification, tells us if the image is upright or inverted. So here's some notes about real images. They're formed where rays converge. They're always inverted, so they're always upside down, and they can be seen on a screen. They can be projected, okay? So just, you can see both real and virtual images, but you cannot project virtual images. And there's never any back ray tracing like what we showed with the diverging lens. So virtual images are a little bit more complicated. You still want to follow these three rules, where if a line comes in straight or parallel, it goes through a focal point. If it goes through one of the focal points, it goes out parallel, and if it goes through the middle, it stays the same. But this gets a little bit more complicated with these virtual images. So you can see the way that we do this, right? You can see this one, if you have a line that comes in through the near focal point, right? So this is your object, and it goes out parallel. But in order to do this, to make it work, you can see this line has to be back connected to the focal point, okay? Because this is actually the start of the image, so it goes, the actual ray goes like this. So in order to encapsulate this focal point, you have to do this little dotted line thing. Okay, so the middle one is simple, right? If this goes through the center of your optical axis in your lens, then that doesn't change. But then in order to get the image, you still have to backtrace to figure out where all the rays converge. Because these rays coming out, if you're over here looking at them with your eyes, then what you see is where all of these images come together back here. So in order to get this point, which is this is your arrow for your image, you have to do some back tracing. So your original rays come this way, and so this one counts as the near focal point, it comes out this way. This one counts as the far focal point, it comes this way. Okay, so it goes like this, and then you trace it back here. And this one counts as going through the center, and then you have to back trace it here. So you can see for virtual images, there's a lot more back tracing that has to happen. So the image is formed at a point from which the rays appear to diverge. So this little pink arrow back here, that's where the point looks to the person. Okay? It's always going to be upright, and it can't be used to produce an image on a screen. So this is like looking at yourself in a mirror. You can see a little version of you behind the mirror, but it's not real, okay? And so back tracing rays really is going to tell you, when you have to draw these sort of dotted lines, right, that's really going to tell you that you have a virtual image. And once again, we follow these three special rays. So parallel rays diverge out, okay? Rays that would pass through the far focal point come out parallel. So you're still dealing with two special rays that have if you're going through the focal point, you either come in or go out parallel, and then anything that goes through the center stays the same. So remember, diverging lenses always produce virtual images because they can't converge rays to a point that you can project on something. So they're not focusing light to a point that you can put on an actual screen. So let's try a clicker question. Take some time and think about this, and then vote. Okay, so this is going to be E. There will be no image at all, and that's because, look, if you remove the lens, it's just like shining a flashlight. You might see some dim version of the image, but you're not going to see a nice focused image. Okay? So the rays are all diverging. They're not focusing to a point, so you might see something really faint and blurry, but it's not going to be even good enough to see. So the lens maker's equation looks like this, but the key here is that we want to figure out how to find the focal length for any lens. So the thing that to keep in mind here is this F is the focal length. All right, this is the index of refraction of whatever the material the lens is made out of. And then we have R1 and R2. Now those get a little complicated. So here's sort of our object, and then we can backtrace to an image, okay? And this is sort of our ray tracing for our two focal lengths. So here's our object, here's our virtual image, and here's our image. And really we're just talking about these as basically two surfaces of refraction. But the key here for the equation, because this is the final image, is that we really want to know about these radii. And this is what we mean when we say the radius. Now this is going to be radius 2, okay? And radius 2 is the one over here, so it's the second one. And when we're talking about radius 2, that's the radius of this circle. So obviously if you make the circle smaller, that's going to make the lens more bulgy. If you make the circle bigger, that's going to make the lens less bulgy. And so what that means is if you wanted to make, like let's say one side of your lens is completely flat, what would the radius be? Okay, so you want to make it bigger and bigger and bigger. That means for a flat surface, you have a radius of infinity. All right, so here's radius 2, and over here is radius 1. And we're looking at these radii relative to the location of the object. So the first circle, so the first part of the lens here, right, this is radius 1 because it's the area closest to the object. This is radius 2 because it's farther away from the object. So radius 1, then radius 2. So you're going in this direction from the object, okay? And the only other thing to remember is the signs. So for the radii, if you're convex toward the object, like for instance this is convex towards the object, that means radius 1 would be considered positive, okay? And for radius 2, it would be concave, meaning sort of circular towards the object, like a cave going around the object. That means that would be negative, okay? Now, we know for the focal length, positive means a converging lens and negative means a diverging lens. So that's all we're keeping in mind here, okay? All right, so that's the lens maker's equation. For thin lenses, we also have this other equation, which is the thin lens equation. And it's pretty simple. It's 1 over the focal length is equal to 1 over the object distance, meaning the distance from the object to the lens, right, S, plus 1 over the image distance, which is the image from the lens, the distance from the lens to the image. Now the distance from the lens to the image varies because in this case, for a real image, you're going to have a positive S prime, a positive distance this way. But if you had a virtual image, like you had a tree over here, then you would end up with a negative S prime. Okay, so this is going to always be positive for a single lens system, but this can be positive or negative based on whether you're on this side of the lens or that side of the lens. So if your image is on the opposite side of your lens from your object, then you're going to end up with a positive S prime. If you're on the same side of the lens as your object, you're going to get a negative S prime. Okay, and this goes back to our magnification, which is negative S over S prime. Once again, here is our little key for figuring out what the signs should be. So remember, we're going to consider the front side of the lens. That's where the object is. So we're always worried about the object in question, okay? And that's how we determine the sign. So here's a problem. Okay, so we have a microscope that uses a plano-convex lens. So here is what a plano-convex lens looks like. This part right here is the plano part, and the convex part is the curvy part. So we're going to color that in. That's our plano-convex lens. Okay, and so we're going to make our optical axis look like this because this is a microscope, so we want to make sure it looks like a microscope. So that means our object is going to be somewhere down here. Okay, so the flat side, this is our specimen. So the flat side, the plano side, is facing the specimen. We know a real image is formed 160 millimeters behind the lens when the lens is 8 millimeters from the specimen. So we know somewhere back here we have a real image. And if we want to draw out the distances, this distance from our lens, this is going to be S prime, which is equal to 160 millimeters. And this is going to be our S, which should be equal to 8 millimeters. Alright, so that's our distance from our lens. So here's our object distance and here's our image distance. Alright, and we know that the N is equal to 1.5 for glass. So we're going to use that for our lens maker's equation, and we want to know what's the radius of the lens's curved surface. Okay, so here we have to use both the thin lens equation, which looks like this. This is the thin lens equation, and the lens maker's equation, which is 1 over focal length n minus 1 over R1 minus 1 over R2. Okay, so there's some rules about R1 and R2. So R1, that's going to be this side. So we know the radius of this, okay? So if something's more curvy, that means its radius is smaller. If something's flatter, that means its radius is bigger. If something's really, really flat, that means that R1 has got to be equal to infinity, okay? So the bigger the radius, the more flat it gets, so the biggest possible radius we could have is going to be R1. Alright, so we're looking for R2, but in order to find R2, we need to also figure out what our focal length is, or at least what 1 over our focal length is. So we're going to use this equation, and we're going to figure out our object and image distance. So we have 1 over F is equal to 1 over 8 millimeters plus 1 over 160 millimeters. Both of these are positive because remember S for one lens is always positive, and because this is a real image, S prime is also positive. So our 1 over our focal length should give us 0.131 millimeters inverse, which means we solve for R2, and that's going to give us, when we plug in n equals 1.5, we end up with 0.131 millimeters inverse is equal to 1.5 minus 1. That's our n minus 1. 1 over infinity minus 1 over R2. Remember, this is going to go to 0. Our R2 is going to be equal to negative 3.8 millimeters, which means it's a convex radius, and that's what we see here. So this should make some sense, and we're using both of these equations. I'd like you to sort of try this. Mirrors, it turns out, work pretty much the same way as lenses, just you have to not go through the lens. So if you have a real image, it ends up on the same side of the mirror as the object, and if you have a virtual image, it's going to look like it's behind the mirror, because remember, when we look into a regular mirror, virtual images are behind the mirror. But we follow the same 3 special rays, right? If you have one that comes in parallel, it goes through the focal length. If you have one that goes through the middle, then it just obeys the law of reflection. And if you have one that goes through the focal point, it comes out parallel. So we still have the same 3 special rays, and it's the same over here as well. Here's one parallel. You have to backtrace from the focal point, There's the one that goes right through the center, that looks like this, and the one that goes through the other focal point. Okay. Alright, so here's another problem. If rays from the sun shine on a large concave mirror, where will there be a hot spot? Meaning, like, if you have, so think about what you have if you have a magnifying glass and an ant, but think about that if you're dealing with mirrors instead of a magnifying glass. So where would be the part where you fry the ant? So I want you to take a minute and think about this. So look, if you have rays from the sun, they come in parallel. So that means the hot spot will be exactly at the focal point. And this is actually a problem in many hotels and modern buildings where we have these beautiful curved shiny surfaces, and then they can, if you stand in the wrong place near the focal point, it will fry people. In fact, there's the Disney Music Hall in LA, when they built that, they actually had to sand down the mirrored surfaces because during certain parts of the day, when the sun hit it just right, they were raising the temperature of certain apartments across the street 20 or 30 degrees in the course of an hour. So spherical mirrors follow the same thin lens equation, and the same magnification equation. The only thing to really remember is the focal length now is the radius divided by 2, because instead of having these two surfaces like a lens, where we have to use the lens maker's equation, we just have one surface. Have these rules for where we get positive and where we get negative. And here's some sign conventions, okay? These are mostly just for your reference when you're making a cheat sheet or trying to figure out how to do a problem. This is how you can decide where the signs should be. Okay, here's one more problem. Please take a minute and think about this, and then we'll go over it. Okay, so we know this dentist is using a curved mirror, so we want to know whether that curved mirror is concave or convex, and we want to estimate its focal length. The information we're given is that we're looking at the back side of the teeth in the upper jaw, so you want an upright image. That should tell you virtual, because remember, real images are inverted. And we want magnification equal to 2.0. This is written as positive because we know that the magnification gives us an upright image, so therefore a virtual image. And we know the mirror is 1.2 centimeters from the tooth, so that is S, 1.2 centimeters. Okay, so we can use our thin lens equation, and we also want to use magnification, which is negative S prime over S. So since we know the magnification and we actually know S, we can solve for S prime, and that's going to give us negative M times S. So that's going to be negative 2 times 1.2 centimeters. So we know that our S prime is negative 2.4 centimeters. Okay, then we can use that to find the focal length. So 1 over F is equal to 1 over 1.2 centimeters minus 1 over 2.4 centimeters, and that gives us a focal length of 2.4 centimeters. Because this is positive, we know this is a concave mirror. So here's our focal length, and it's concave. But just to be clear, let's draw it out. So here's our optical axis. Okay, this will be our mirror. We will draw it like this. Oops, here's our mirror. It's going to look something like, oops, it's probably going to look something like this. This is a concave mirror. We're going to have our tooth. Our tooth will be somewhere over here. It's not a very good tooth, but you get the idea. Here's our distance S, which is 1.2. And our actual image is going to be back here somewhere. This is our tooth at a distance of 2.4 centimeters. This is S prime, and we can see this is an upright image, right? These are pointing the same way, and it's a virtual image because obviously you can't see through this mirror, but the mirror is going to have a focal length of 2.4 as well. Here's a clicker question. So, if a concave mirror of focal length f forms an image of the moon, where is the image located? Well, because the moon is very, 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 very far away, the rays are basically coming in parallel, and if you have parallel rays, that means they converge at the focal point.